When you go online to see the recordings, can you see the ones that are already in the stream recording? You know what I mean? Not sure. There's a way you can go see those, but I've just been posting the links, so that's putting them up on YouTube. We're starting a new unit. I guess it's unit 14, not 13, on phase equilibria. According to our syllabus, we only have 2 units left. This one, which is actually quite short, and organic, which is kind of as long as we need it to be. In previous years, it's actually been cut depending on the particular year. So we're doing fine in terms of how far we are at this point in time. I also wanted to point out that how we had quiz 1, then we had a midterm, then we had the oral last week, and then we have quiz 2. I think there was some discrepancy for quiz 2 where I think it was posted in the syllabus that it was this week, and it was posted in our intro slides that it was next week. So the plan for that is actually next week, not this week. And it'll be similar to the first quiz where it will be you can pick a time during the week to complete the quiz. But once you do start, it's timed. It will likely be covering the 2 chapters, one on electrochem and this one on phase equilibria. And that's likely going to be that. Then it'll be the organic chem, and then kind of a countdown to the final exam at that point in time. So if you have any questions on any of that, please let me know. We can start unit 13 today, phase equilibria and solutions. And, we have a couple of subunits in here. A lot of this stuff, I was going through this, checking through these slides last night again, and I kind of realized like a lot of this content could probably have been spread over some other chapters, because especially when it comes to like the phases and vapor pressure and phase diagrams, it almost could have been the first chapter we did this year, but that's something to think about for the future. So phases is kind of a concept, central concept in chemistry. We've been using this all semester. Basically the concept of a phase as defined here, it's a chemically and physically homogeneous part of a system defined by a definite boundary from other phases. We often call the boundary an interface. And so, if you have oil and water and they're not mixed together, we would say that's 2 separate phases, and there's a definite boundary where those phases start and stop. Ice floating in water, et cetera, et cetera. So the different phases, of course, that we are aware of, that we know we use all the time. It's the gas phase, where if you have 2 samples of separate gases, they can mix completely. This is true for all gases, and there's no phase boundary between them. Sometimes what you can have with gases, though, is called layering, where if you have 2 different gases that are either different temperatures or different densities, well, if they're different temperatures, they will be different densities, then you can have sort of the denser layer sit on the bottom and the lighter layer on the top. Those will eventually mix, and they will form what we call a solution, but that will take some time. So I guess kinetically they can appear to almost be separate phases. Although in those situations, I wouldn't say there's a definite boundary. It almost sort of one blends into the other. You can have multiple phases for liquids as well, as we had the example of oil and water. As long as there's a definite boundary, like you see here, we might call that the oil-water interface, for example, then we can do this. We actually have a course later on that you can take, I think in your 3rd year, Chem 3143, or is it 3413? I think it's 3413, which is called surface chemistry, which is really the chemistry of what goes on at the interface between different phases. Because if you think about it, if you have like a glass of water like this, that says water and ethanol, but what happens is water molecules that are kind of in the center of a phase are quite different than the ones that are at the edge, at the surface, because the ones in the middle are surrounded by other molecules, which allows it to maximize its intermolecular forces, whereas the ones on the surface can't have any interactions, with the molecules of the separate phase. So what ends up happening is they orient themselves typically in very specific ways along the surface, which can lead to some very interesting phenomena. So for example, in water, one of these phenomenons is surface tension, where surface tension is a function of the fact that the water molecules don't like to sit at the surface. So they'll act to minimize that surface as a result. It's almost like, bees. When you have bees, well, of course you know bees. In the winter, what bees will often do is kind of form like a ball, and in the middle of the ball, the queen will be there, and the others kind of are constantly moving and buzzing around, and they are generating heat to keep the queen warm. And the ones on the very outer edge are the coldest because they're exposed to the elements. And they don't like that. They're constantly trying to like crawl inwards, which, if one of the outer ones goes in, that means one of the other bees ends up on, there's always got to be bees on the surface, but none of them are kind of happy on the surface. And what kind of naturally happens to that ball of bees is it forms a sphere, because in a spherical shape, you have the fewest number of bees on the outer surface. And you can think of water molecules as being a little bit like that. They don't want to be on the outer surface either because they can't have complete intermolecular forces. So the whole shape will adopt a geometry that minimizes the number of ones on the surface. So when you have water falling as a raindrop, they make little spheres. Sometimes elongated spheres because of the drag of the air, but you get the idea. We call liquids miscible if they are soluble in each other. And if they are not soluble in each other and separate into different phases, we call them immiscible. So typically when we use the word miscible, we mean that they can be mixed in any proportion. So an example here would be water and alcohol. You can have any amount of water and alcohol put together. And when I say alcohol, I mean like ethanol. They can be mixed in any amount. Of course, for them to be miscible, they need complementary types of intermolecular forces. Mixtures that will not completely mix, maybe they'll be like partly soluble in each other, but eventually they'll separate into phases. We call them partially miscible. All right. So this is so I teach Chem in Our World, and in Chem in Our World, this time of year, I'm getting people to do, they do chem demos in videos. And this is a very popular one where you take, that blue is food coloring with just water, and on top is vegetable oil. It's got a bit of a yellowish color to it. And you can drop a little Alka-Seltzer tablet, those little things, which is basically bicarb and citric acid, which when you get them wet, they will react to make carbon dioxide and sodium citrate, so it starts to bubble. And the bubbles carry up bits of the water, and they call it like a lava lamp, which is, I guess, somewhat like a lava lamp in that you have two phases that are separate from each other. But this is just a neat example, I think, of immiscibility of two separate liquid-liquid phases. Solids, a core solid is its own phase. Solids exist, they can exist in a number of different forms. So if you have the same chemical material in multiple different forms, sometimes we call these polymorphs. It's a crystalline material. And so calcium carbonate, these are two different polymorphs. They're both calcium carbonate, both crystalline solids, but they're crystallizing in different crystal patterns or different crystal structures. I have a very interesting story actually about polymorphs. There was a drug company, and I'm going to forget the name of the company and the drug. This was back, I believe, in the 1990s, where they produced this drug that was a blockbuster drug, and I forget even what it was used to treat, but they were making like over $1 million a day off of this particular drug. And they had this big factory, I believe in New Jersey, that they were producing big batches of this drug, and then, they'd chemically synthesize it. In the end, they had this white powder that they could put in a pill, and you give people the pills, and it would treat whatever it was designed to treat. what was happening, they have been selling it now for years, making a huge amount of money, and I think they had finished something like 85 batches of this particular drug, and a batch was like many kilograms of this drug. So like they're making it on a huge scale. And they went to make like the 86th batch, the next batch. And what happened is in the step where the final product solidifies, it solidified into a different polymorph that time. So the first 85 times, they got a single polymorph or a single crystal structure for the drug. That next time, 86 or whatever it was, they got this second polymorph form. And what happened was this new polymorph was really not very water soluble at all. And so what that meant is if people ingest this as a pill, the bioavailability of the drug was very low, and therefore it wasn't having really any therapeutic effect. And so basically the whole batch was a waste. So what they did is they dumped the batch, they cleaned out all their equipment, and started again. Every batch from that point on was the undesirable polymorph. And they tried again and again. They tried to clean it super well. And what they figured was that the new polymorph was thermodynamically more stable than the initial one, but that given a choice, the other one was formed, it was formed faster. So it was sort of the kinetic crystal form was the one that they were trying to get. But once they formed, for the first time, the thermodynamic crystal structure, from that point forwards, you couldn't form the other one anymore, because if there was tiny, tiny amounts of the thermodynamically stable form around, it would sort of seed formation of more crystals. So if they would have to get rid of every possible microscopic seed crystal of the stable form in order for that polymorph not to be formed anymore. And so their solution was, well, let's just build a whole new factory. And if you think that's extreme, just realize that, $1 million a day pretty quick, and it was probably multiple $1 million a day, pretty quickly pays for the new factory. And they were running out of their stock, and they were getting a little bit desperate. So they actually made their new factory in Italy and built it, did the first batch, and they got the undesirable polymorph in the first batch in the Italy factory. And they scratched their heads and tried to figure out why that was. And it turns out that they had, during the construction phase, had some engineers that had traveled back and forth between the two plants. And they think that some of the engineers from the original plant may have carried seed crystals across to the new plant just by being in their hair or in their clothes or on their skin. So it just takes a tiny, tiny one, and it basically ruins the whole plant. And it turns out they never solved the problem. And the way they ended up solving it is, and it took them a while. This drug was off the market for a while they tried to solve this problem, and then they had to go through the regulatory process again. I forget exactly what they did. They ended up either somehow putting it into a gel and having the gel be in those sort of large capsules. And so that it was a completely new formation, but a completely new basically way of putting the stuff together. So yeah, polymorphs actually can have very different, even though they're the same material, can have very different physical properties. And hopefully, as that story shows you, in medicine, that can be a very important thing. Allotropes are another similar but different concept of polymorphs. Allotropes are basically different physical forms of the same pure element. So we use allotropes when we're talking about pure elements, where polymorphs, that really refers more to compounds, like calcium carbonate. Allotropes is when you have the same element in different forms, like graphite and diamond. There's many other allotropes for carbon as well, such as, we often call these fullerenes. An example is buckyball C60, which is often called Buckminster fullerene. And we can have nanotubes. We can have a lot of just pure carbon-based materials that can be made and used. We call those allotropes. Phosphorus has 3 different allotropes: white phosphorus, red phosphorus, and black phosphorus. These are all pure elements, but different crystal forms. So I guess they're sort of also polymorphs and allotropes at the same time, because they're all solids. White phosphorus is the one we see here. White phosphorus is the form of phosphorus that was the first discovered form of pure phosphorus. Do you know what it was derived from? What material? They got it from urine. And the story goes like this. It was a guy named Hennig Brand who isolated it for the first time. He didn't recognize what it was. He was an alchemist. So this is sort of before chemistry became a thing. And alchemists were obsessed with a number of things. Some of them were purifying chemical substances, putting them in a pure chemical form. But one thing definitely is they were shooting for, let's say, the elixir of life, which was a potential, drink that you could drink and it would make you immortal. And they were also interested in converting what was called base metals. These were common metals, things like lead, into gold. And those weren't two separate endeavors. Those were actually the same. They thought of it the same way. They thought gold was just like any other metal, but immortal. And they figured if we can figure out how to make metals immortal by turning them into gold, we can figure out how to make people immortal by giving them the elixir of life. And they believed in a substance called the Philosopher's Stone, which would convert water into the elixir of life and could also somehow turn base metals into gold. So Hennig Brand recognized that gold was special. They all recognized gold was special because it's the only metal that they knew of that didn't oxidize. So it was perfect for jewelry and things like that because it would last forever. And we know from their previous chapter that means it's just going to be very high up on the electrochemical series, really, really badly, wants to be reduced if it's in its ionic form. So they also recognized, or this guy recognized, that gold was different in color than pretty well any other metal that they knew about. Certainly brass and copper are colored, but every other metal they knew about was sort of like silvery color. And they figured maybe whatever makes gold colored is also what makes gold immortal, last forever. So they had a connection between the color and the immortality of the substance. And then they realized, or Hennig Brand realized, that human beings, every time they go to the bathroom and pee, the pee is gold. And he thought maybe whatever's making the pee gold is what's causing us to be alive. And every time you pee a little bit of that out. We lose a little bit of our immortality. And then we age, we get older, we slowly break down, and then we die. And that's when all this yellow stuff is gone. So what he decided to do was collect a bunch of urine and then see if he could isolate from the urine whatever made it yellow, and therefore that would be sort of the essence of life. And so what is in urine is there's lots of phosphates, right? There's lots of phosphates in our urine, and there's also a lot of carbon-based compounds, like urea would be an example. And what can happen is you can have a reaction with carbon-based compounds to make P4 plus CO2. And that's obviously not balanced. And, there's other stuff attached with the carbon. But it made this waxy material. So he basically took like dozens of liters of urine, I don't know how he collected it all, and boiled it down until it became like a thick paste, basically boiled all the water out of it, heated it past that point until this chemical reaction started happening. And he noticed this formation of a white waxy substance, looks like this. And he picked that out with tongs, and as soon as he pulled it out of the flask, it burst into light and then disappeared. And because P4 will react very rapidly with oxygen, P2O5 plus light. Very, very bright. Now, he thought when he pulled this thing out that had a big bright burst of light that he had discovered the essence of life. He discovered phosphorus, which is pretty cool too. But anyway, that's that material there. So phosphorus, white phosphorus, because of this particular reaction, that is actually like a white powder. And if you take white phosphorus and melt it and then spray it into the air, it'll make what's called a smoke screen. So white phosphorus is still used for military applications. You can spray it out of a plane and create a smoke screen. And then if you have troops drop from the plane, parachutes, they can't really be targeted easily because they can't be seen easily. I don't know how much of that goes on today, but that is one military use. It was also used during World War II, actually, because it also gives heat. And I think the Germans did this in England, where they would drop white phosphorus over towns and chunks of it. And when it landed on a roof or wherever, it would just instantly catch on fire. And what you would do if something caught on fire is you would put it out with water. And water will put the fire out here, but as soon as the fire dries, if the phosphorus is still there, it'll reignite. So the only way to stop the source of the burning of the fire was to find all the little pieces and have them safely disposed of. Just spraying and putting out the fire wasn't enough because it would reignite once you found the source again. I believe it's banned now. I think it's considered a chemical weapon, and so it's banned by some international treaty. All right. Vapor pressure, and this is funny, we've talked about vapor pressure quite a bit. What we do know, though, is that vapor pressure of any, so if you have a liquid, right, and you have a liquid in a container and it's in contact with a gas phase, which would be ordinarily the case if you have an open container or even a closed container that's not completely filled. What will happen is, if you look at this example, this is water in a closed container, and this would be like the surface of the water right around here, is molecules will leave the surface and enter the gas phase, and gas phase molecules can also re-enter the liquid by colliding with the surface of the liquid. And when the rate of evaporation is equal to the rate of condensation back into the liquid phase, we say that this has reached equilibrium, right? And what happens at equilibrium is then you have a constant number of molecules in the gas phase. They're certainly entering and leaving the gas phase, but those are happening at the same rate. And so we have what we call a saturated vapor pressure, P0 vap, which we call the equilibrium. We call that the vapor pressure of that liquid. And it's characteristic of any liquid what that pressure is, depending on the temperature. At different temperatures, the pressure will change, but for water at 40 degrees, that pressure will always be the same, that partial pressure of water. For open container, it's not quite as simple, I guess, because the water, once it exits the surface of the liquid, can then just go off and never return. And so for that reason, it doesn't really establish an equilibrium. And usually, depending on the humidity, usually what would happen with that container is it would just evaporate until the container was empty. So we have a word that means volatile, or it's called volatile, which basically it's a description of a liquid which is telling you how easily that liquid will evaporate. And I don't know if there's a hard definition of the word volatile, but generally what it means is if a liquid or a substance is volatile, it will have a higher vapor pressure at equilibrium than water. And if something has a lower vapor pressure at equilibrium than water, we would say it's non-volatile or not volatile. So some things that are volatile, like gasoline, nail polish remover, which is often acetone or ethyl acetate, or a mix of the two. Both of those are volatile. There's many volatile substances in perfumes, so that's what you're smelling. Alcohol is volatile, so if you ever are getting an injection and they rub your arm to get the to disinfect it before you get the shot, that's a volatile liquid as well. Great. So basically, this is just saying that evaporation from the surface or evaporation of a liquid is a surface phenomenon, meaning only molecules that are at the surface can exit the phase, which really means that the rate at which something evaporates is a function not only of its equilibrium vapor pressure or how volatile it is, but also how much surface area there is exposed. So if you have water in like a narrow, tall bottle, it'll take forever to evaporate all of the water that's in there relative if you poured it out on a big flat surface where you have a lot more surface area. Also, the temperature matters. Higher temperature means higher vapor pressure, which means there's more molecules at the surface with the energy to leave the solution, which means faster rates as well. You can also have a vapor pressure over a solid. This is typically less of an issue. It's important for solids, I would say, that can undergo sublimation, like dry ice, but it's normally something that's very low. Most solids don't have any significant vapor pressure. Dry ice, snowballs. So actually, if you take snowballs and freeze them, I used to do this as a kid. I don't know why, I just figured like in the middle of the summer, you could go out and get a snowball. They will disappear in your freezer. And that's because there is, for a solid, vapor pressure, and freezers are built today to reduce vapor so you don't have frost buildup. And so these will shrink away if you just leave them by themselves in the freezer. Although if you put them in a bag, maybe they'd last. Try that. Ice cubes as well. If you have an ice cube tray just sitting out in the freezer, the ice cubes will shrink down eventually, slowly into nothing. And that's because, you know, you can go directly from the solid phase to the gas phase, and there is vapor pressure over the solid as well. You like Eggos, I see, and M&Ms. So we define boiling point, and I think we've kind of talked about this. We define the boiling point as the normal boiling point is the vapor pressure. When the vapor pressure of that liquid reaches 1 atmosphere, then that's what we call the normal boiling point. And I believe this is one of the few definitions that has not changed from atmospheres to bars. Almost everything else used to be atmospheres and switched to bar, and we've been using bars all semester, but I think the definition of normal boiling point is still in atmospheres. I think the reason for this is because we picked a nice round number for the boiling point of water of 100 degrees Celsius. And it's really awkward, I think, if we had to change our boiling point for water to like 101 degrees or something like that. So we use atmospheres. The boiling point, or you know, the non-defined boiling point of a substance is the temperature, and when we say the point, this really means the temperature where the vapor pressure of the liquid is equal to the external pressure. So what that means is the boiling temperature of a liquid will depend on the external temperature. And we take advantage of this all the time. So if you have a low pressure, it'll boil at a much lower temperature. So we have actually a machine that we use all the time in organic chem. We call it a rotovap. And the purpose of a rotovap is to rapidly evaporate excuse me, I promise that was not COVID. To rapidly evaporate solvent away from a solution. And it kind of looks like this, where you have a bulb where you have your solution in there. And then it's connected. There's a machine here, first of all. And then it has up here, it has a coil. And a coil is like a glass coil, and kind of goes in the center as well. So you can have cold water in, and then you can have the water that's gone through the coils come back out. This whole thing is under vacuum. This flask is rotated, and this is put in a hot water bath. This will have a collector down here. And the idea is, with this thing, you rotate the flask, it spins around, it coats the inside of this flask here with the solution itself. So you get a big surface area of the solution. It's sitting in hot water or warm water. So that warms up the liquid that's in the solution. And then the whole system is put under vacuum. And when the whole system is put under vacuum, what that does is it lowers the boiling point of the solvent on the right-hand side. So it boils at a very low temperature, it evaporates very easily. The vapor travels up here towards the vacuum. It goes across these cold coils and then can condense. And if it condenses back into a liquid, it'll drip down here and fill that up right there. So very rapidly, what it'll do is it'll transfer the liquid here into that container. And when this is done, what you're left with in your flask over here is kind of just like whatever solid was dissolved in that liquid. So this whole process makes use of the fact that if you lower the pressure, the external pressure, that will lower the boiling point. And if you raise the temperature, that will lower the boiling point as well. And when I say this is quick, usually what that means is like less than 10 minutes. Or if you let that flask just sit out on the countertop to evaporate on its own, it could take days. Great. So yeah, evaporation takes place on the surface. The difference between just regular evaporation and boiling is when bubbles start to form at the bottom. It's very, very simple. And bubbles form, they rise. One thing that you'll notice, if you see this, boiling water, if you actually take a pot of water and you put it on the stove and you put the heat under it, what you'll notice is initially the bottom of your pot will have like little tiny bubbles that are kind of like clung to the bottom. It's not rolling, it's not boiling that way, but gas has formed and it's kind of sitting on the bottom. That is not boiling. What that is gas that's dissolved in the liquid is separating out as a phase. Because we know the solubility of a gas in a liquid decreases as you increase the temperature. We're gonna deal with that in this chapter. So what happens if you add salt or anything dissolved in the water, that will increase its boiling point, but it doesn't increase it by a lot. So one thing a lot of people will suggest is if you're cooking pasta, put salt in the water because it increases the boiling point and therefore makes it cook faster. It turns out that it has like basically zero effect. Unless you put in like a kilogram of salt, then it'll raise the temperature by like 2 degrees. You know what I mean? Like it doesn't raise it by a whole lot when you're talking about salt. If a higher temperature to cook it faster is what you want, you would want to go to a higher pressure. And that's what happens in a pressure cooker. So in a pressure cooker, you can usually go up to like 2 atmospheres, and that causes the boiling point of water to go up to about 120 degrees Celsius. And so pressure cookers, if you do that, you can cook food a lot quicker, especially things like potatoes or things that could take a long time. The other thing with a pressure cooker is it's often used if you're making preserves, and that's because there are microbes that are not killed with boiling at 100 degrees Celsius, but are killed between 100 and 120. So I think botulism is one of them. Pretty tough to survive 100 degrees Celsius, I think, but there you go. So this is what I meant with that picture. When you first start heating water, and you can start to see those little bubbles form at the bottom, that's not boiling. That's just air that's in the water that's no longer soluble when you warm it up past a certain point. I've heard it said actually that the fishing in our part of the world around here is best in anywhere in the world in terms of amount of fish that can survive in a given space of water. And it comes down to the temperature, because it's warm enough for enough organisms to survive and provide food and so on, but also the temperature low enough that oxygen is soluble enough to permit larger animals and a lot of life to live. And that if you go to warmer water, the actual amount of oxygen that's soluble in the water goes down, which makes it more difficult for certain fish to survive. There is a quantitative relationship between vapor pressure and temperature, and this is I'd say a very useful relationship, because in a lab situation, it's very important to know practically what the vapor pressure of a substance is going to be depending on the temperature, because it basically will tell you, if you're doing a chemical reaction inside a reactor, let's say a stainless steel reactor, and you want to heat it up to a certain point, using this equation, you could calculate what the pressure inside that reactor would reach. And that's important because you need to know if this reactor can handle that pressure, and whether the whole thing is going to blow up or whether it's going to be just fine and move forward. So the way this equation works is you need a reference pressure and temperature, which we'll call P1 and T1. And if you know the delta H vap, most commonly, occasionally I guess you can use sublimation as well, but if you know the delta H vap, you can then use this to figure out what the pressure and temperature will be at new values. So if you increase the temperature by 40 degrees, you can figure out what the new vapor pressure of that substance is going to be. This is also useful in the up or down region. You can figure out for water, you take water and it's like, let's say we're going to heat water to, 80 degrees. What's the vapor pressure of water then? Or you could look at it from the opposite perspective. We're going to put water under a pressure of 8 atmospheres. What will its boiling point be? Right? These are the kinds of things that you can figure out. We can look at an equation like this. We say the normal boiling point of benzene is 353.3 K, and the enthalpy change of vaporization is delta H vap plus 30.8. Calculate the boiling temperature of benzene at a pressure of 5 kilopascals. I just need to bring up my my numbers here. I don't have, obviously, the numbers in my head. Okay. Okay, so the equation that we have is the natural log P2 over P1 minus delta H, which is usually delta H vaporization, over R, which is the gas constant, 1 over T2 minus 1 over T1. Okay, so we're saying that the normal boiling point, TB, 353.3 K. Why don't we call that T1? What's P1? Well, P1 is defined as the, well, it's obviously the pressure that goes with that temperature. And if that temperature is the normal boiling point, then we know that that normal boiling point is 1 atmosphere. And if we want it in kilopascals to match our unit here, we can do the conversion. So P1 is 101.3 kilopascals. Okay. It wants us to know what the boiling temperature is going to be at P2. Question mark there. So what we can do is just plug all the numbers into our equation, and we're going to end up, the only unknown that we have in this situation is this T2. So you can kind of plug in the numbers and then solve for what's missing. So if you have the natural log P2 over P1, and these are both in kilopascals, which will cancel, equals minus delta H I'm going to put this in joules because R is going to be joules per k-mole times 1 over T2 is our unknown minus 1 over. And you can just solve here for T2 and you get 274K. So the pitfalls to watch out for when you're using this equation, make sure your 2 units of pressure are in the same units. Make sure that your delta H is in the same units as your R, and temperature has to be in Kelvin. Other than that, it's and also make sure that your P1 and T1 fit with each other, that you form the pair, right? That you don't mix P1 and T2 and P2 and T1. Cool. Doing good. Now, every substance will have, I guess, or will exist in different phases at different conditions of temperature and pressure. And what we can draw is a diagram called a phase diagram, which shows us what phases a substance exists as depending on the temperature and pressure that it's under. So here's an example where if you take dry ice on the left and water on the right and put them both on a surface at room temperature under the exact same conditions, they will undergo different phase changes. One will undergo sublimation on the left, one will undergo melting on the right, and it depends on the particular substance what will happen. And that's all represented in a phase diagram. Phase diagram looks like this, where we have pressure on one axis, temperature on the other axis. And we have these lines which represent a phase boundary. We have another boundary here. So what this means is if you are somewhere out here in that zone of temperature and pressure, then this particular substance represented in this diagram will be a gas, right? And if you increase the pressure or decrease the temperature, you can move into another phase potentially. So if you're right here, for example, at this point, that specific pressure and temperature, if you increase the pressure, you can compress that gas into a liquid. And this is what happens in many cylinders. When you get those big cylinders, like let's say a cylinder of propane you'd get for your barbecue. It's a gas at ordinary temperatures and pressures, but then if you compress it, it will, under higher pressure, turn into a liquid. And you can slosh it around and feel the liquid inside in there. The other thing you can do with the gas is you can cool it, lower its temperature, which is going that way, which you can cross that boundary as well. And if you're in the liquid phase, like out here, some liquids can be compressed into a solid. Some of them can be cooled. Almost all liquids can be cooled and turned into a solid as well. So this is an interesting point right there. That's called a triple point. If you're on anywhere along one of these boundary lines, one of these blue lines, all of those represent a point of equilibrium between two phases, right? So if you were here, exactly, you would have, that would be describing pressure and temperature where you have an equilibrium between solid and liquid. An example of an equilibrium between solid and liquid is a glass of water with ice cubes in it. You have solid in there, you have liquid in there, and if you thermally isolated that, if you put it in a thermos, what would happen is the ice amount of solid and liquid would not change over time. And you might have some freezing and some melting occurring, but they would be at equilibrium with each other. So that would describe a situation along one of these lines. This point here, which I've pointed to here, is what we call the triple point. It's T right here. The triple point is the point for a substance where the solid, liquid, and vapor are all in equilibrium with each other. And there's only one such temperature and pressure for any substance in which all three of those can be all in equilibrium together at the same time. So essentially what's happening is it's freezing and boiling at the same time. It's kind of a weird thing to think about, but it's exactly what's being described at that particular point. Now, water is weird. Water has a weird phase diagram, which is actually really important for the existence of life on our planet. This diagram that you see on this page is very typical for a normal substance. Basically, what this means is this blue line right here slopes off to the right, which means if you have a liquid at a temperature and pressure right here, and you compress it, and you increase the pressure, you will go vertically here, and you'll compress that liquid into a solid. Nearly every substance can have a liquid compressed into a solid. Water is different. Water, instead of veering off to the right, notice it veers off to the left. So what that means is you can't compress liquid water into ice. If you're over in the solid phase, in fact, in the ice phase, and you compress it by increasing the pressure, you actually push the solid into the liquid phase. You melt ice by compressing it. And this is the whole idea behind skating. You know, when you're on skates on ice, you have a high pressure placed on the ice where the blade meets the ice, and that will cause the ice to melt at that point in time, which lubricates the movement of the blade across the ice. Same thing with skis. Of course, skis don't put as much pressure on the solid water, the snow and the ice, as skates, but same basic principle there. What this also means is that when water freezes, it takes up more volume. Because if water didn't take up more volume as a solid, then you could compress it into a solid. But if the liquid phase takes up less volume for a given mass than the solid, then that's describing the situation we have right here with water. And we know this, if you freeze water into ice, ice floats, right? That is a very unusual feature of water. Almost every other substance, if you freeze it, you form a solid that's more dense that sinks to the bottom. And if you think about that, you know, when we went through an ice age here 10,000 years ago, if you had water that froze on the surface of the ocean and it sank down to the bottom of the ocean, exposing more water to freeze, then the oceans could potentially freeze all the way through. Where that's not what we see. And even in a deeper lake, it will not freeze all the way through here during the winter. It'll form a coating of ice along the top, but you know, even during the coldest spell, if you go to like the Wolfville Reservoir and you drill down through the ice, you'll find water, which is necessary for anything that's living in there. A lot of things have not adapted to being completely frozen all the way through for several months of the year. So that's all because of this one property of water, and it's indicated in the phase diagram where if you look at the vertical line right here, if that solid liquid equilibrium line veers to the left of that, you have a substance like water. If it veers to the right, which is almost every other substance, then the solid will be more dense and it'll sink. Another point, we have the triple point, we have these individual lines which represent equilibria. We also have this point C, which we call the critical point. And the critical point is the point above which, so if you're at a higher pressure or temperature than that, there's no difference anymore. There's no separation between the gas and the liquid phases. So you can't evaporate something anymore or compress a gas into a liquid anymore if you're above the critical point. So when we see these phase diagrams, often this critical point just sort of like ends. Okay, so another way to think about this is if we draw kind of a vertical point here, anything in this zone is often called a supercritical fluid. So a supercritical fluid is arguably a new phase, but it's got properties of a liquid phase and it's got properties of a gas phase. And what makes it like a gas is that it's completely miscible with everything else. And what makes it like a liquid is that it has very high solubilizing power. You can dissolve a lot of things in a liquid, but not in a gas, where supercritical fluids can dissolve a lot of things. There's kind of a picture here. There's a liquid and a gas, and this is if the temperature of this is below the critical temperature. If you start to heat this up, what happens is you can get a phase change, you can get some boiling in there. We're looking through like a little glass window. And once the temperature reaches the critical point and the pressure is able to build up above the critical pressure, we have what's now called a supercritical fluid. It means you're somewhere in this zone up here. So supercritical fluids are used. They're sometimes used to decaffeinate coffee, because if you put coffee beans inside a supercritical fluid, you can dissolve substances from that, like caffeine, and then you can move the beans along. And then what happens is if you lower the temperature or release the pressure such that you go back below the critical point, what happens is all of a sudden it just instantly can become a gas again, and it loses its liquid-like features and it loses all its solubilizing power. And what can happen is whatever was dissolved in there, like the caffeine, comes down like snow. So it's a quick and easy way, and it's just often the supercritical fluid that's used for decaffeinating coffee is carbon dioxide. So it's a very kind of safe, non-toxic material that you can use. The way you can think about a supercritical fluid, I don't really like the way they drew it here. We have your gas phase, we know all the molecules are separate from each other. Liquid phase, where they're condensed, they're close to each other. Solid phase, they're in sort of a rigid packing. Supercritical fluid, I don't like the way they drew it. It's almost more like you can think of them as like little clusters of various sizes of molecules separated by large amounts of space. So it's like gas, where you have like large distances between clusters, but each cluster itself is like a mini liquid droplet. And these can grow, they can merge, they can separate. It's a very fluid system. But it does have those clusters of water, it does have intermolecular forces, so it does have the ability to dissolve things like liquid phases do. So yeah, CO2 is often used to do this, decaffeinate coffee beans and other things like that. Why don't we start here next class? Because I think we went over by a couple of minutes. Things are going good. This chapter is, I'd say, lighter than some of the other chapters that we've done, but it's coming along. All right, so I'm going to stop recording.